everyone, welcome to APS Deep Academy and this is your mentor Swati Joshi. In last class, we completed our discussion on fixed bias technique. We know that fixed bias has few limitations. The first one is it is unstable when temperature varies. And the second one is it is unstable when transistor parameter or beta will change. Now, to remove those shortcomings of fixed biasing, we have emitter bias. Today we will discuss emitter bias. This is the circuit diagram of emitter bias. Emitter bias circuit simply obtained by introducing emitter resistor in the fixed bias. So, till now we study fixed bias, we connect RB and RC and RB and RC to one VCC, and now in this we connecting the RE also. In emitter section also we are connecting the resistance. Now we will discuss how this circuit is overcoming the limitations of fixed biasing. So, before we discuss this, we will discuss a few simple terms, which is nothing but what is the effect of temperature. Okay, what is happening when temperature is increased? So, when temperature is increasing, the leakage current, which is nothing but ICBO, will increase. And if this ICBO or leakage current will increase, it means the IC current will also increase. Okay, if IC current will increase, it means IE current will also increase. Why so? Because emitter current is nothing but collector current plus base current. So if IC is increasing, IB is also increased. If this IE is increased, so voltage drop, which is nothing but VE, which is IERE, will also increase. Okay. So what is happening due to the process of change in temperature or temperature increment, the leakage current is increasing. And if leakage current is increasing, the collector current is increasing because it is the output current. And when circuit is producing more current, then the output current will change. So IC will increase. If this IC will increase, the emitter current will also increase, which is because IE is nothing but IC plus IB. If this IE will increase, the voltage drop across this resistance will also increase, which is nothing but the IERE. If this voltage is increasing, it will affect the base current. Okay. If this IERE will increase, it will make the base current slow down or base current will decrease. We will see how this is happening. And if this base current will decrease, it means the collector current will also decrease because collector current is nothing but beta times base current. Okay. So this is the whole term happening in emitter bias circuit. And first we will discussing the temperature variation. So if temperature increase, leakage current increase, collector current increase. Due to this emitter current increase and due to this increment, the voltage drop across the emitter section will increase, IERE increase, and this increment, due to this increment, IERE increment, the base current will decrease and the collector current will also decrease. Now we will discuss it in little detail what is happening here. Okay, now we will apply KVL in this input side. Okay, so if we apply KVL in input side, what we will get? VCC is nothing but IBRB plus VBE, voltage across this base emitter, plus IERE. Okay, so this is the KVL of this loop, input loop. Now we have what we want? We want IB. So IB, what is IB? VCC minus VBE minus IERE upon RB. This is our IB. Okay. From this equation, we calculated the value of IB. So here we can see that this IB, if IERE is increasing, it means if IERE is increasing, this IB will decrease. In this equation, we clearly see that because IERE is in negative. So if negative value increase, it means the IB will decrease. Okay. So this is the first term we calculated here, that due to the process of temperature variation in emitter bias, the collector current will not change because IB is reducing. So the IC will also reduce. So IC is nothing but beta IB. It means if IB is reducing, the IC will also reduce. So in this manner, this emitter bias section is controlling the temperature dependency of the collector current. Okay. Now we will check for the current gain beta. Okay. For current in beta, similarly we will apply the KVL in the input loop. So VCC is nothing but IBRB plus VBE plus IERE. Now we will equate this equation towards 0. So VCC minus IBRB minus VBE minus IERE equal to 0. Now this is emitter current, and emitter current is nothing but collector current plus base current. So we will make this collector current plus base current. So this is nothing but IC plus IB into RE equal to 0. Now what is happening here? IC is nothing but beta IB. So similarly we can change the value of IC and replace it with beta IB. So IC is nothing but beta IB plus IB into RE equal to 0. Okay. Now we will further solve this equation. What is happening here? Now VCC minus IBRB minus VBE minus, here if I do cross multiplication, what will happen? Beta IB into RE plus the second one is IB RE. Now we will further solve. What we will get? VCC minus IBRB minus VBE is nothing but, if I calculate, take common here, IBRB we will take common here. So this is nothing but beta plus 1 equal to 0. Okay. So now from this equation and this equation we can take common IB. So VCC is nothing but IB we are making common. So here RB minus minus plus RE beta plus 1. And here this is also minus VBE equal to 0. If we further solve, what we will get? We will get the value of IB. So in this equation, what is the value of IB? VCC minus VBE equal to IB RB plus RE beta plus 1. So the value of IB is nothing but VCC minus VBE upon RB plus RE beta plus 1. Okay. Now this is the value of IB. Now here we have to consider few terms. First one is for beta. Beta is very greater than 1. Okay. So beta plus 1 we can consider simply beta plus 1 as beta. Okay. So now IB is nothing but VCC minus VBE upon RB plus RE into beta. Why so? Because beta is very greater than 1. It is current gain, it is very greater than 1. So beta is very greater than 1. So beta plus 1 we can simplify this beta plus 1 as beta. So this equation we have VCC minus VBE upon RB plus RE into beta. Now the second term we have this RE also and this RB also. So this RE resistance is very greater than RB. So we can neglect the RB resistance also. Why so? Because this RB resistance is very small. If we consider the value in earlier also, we see that one is in kilo ohm and other one is ohm. So RE resistance has very bigger value than the base resistor. So what is happening? IB is nothing but VCC minus VBE upon RE into beta. So this is the value of base current here. So we know that collector current is nothing but beta into IB. So IC is nothing but beta into VCC minus VBE upon beta into RE. This is the value of IC. So here we can see that this beta and this beta can be cancelled out. So IC is nothing but VCC minus VBE upon RE. From this equation, we can see that now IC is independent of beta because beta cancel out. So IC is nothing but the value of VCC minus VBE upon RE. So it is depend on the resistance RE, the base emitter voltage and the input voltage, but it is independent of beta. Now beta is not affecting the collector current. So with the help of these two equations, we clearly see that now in emitter bias, the temperature, due to the effect of temperature variation, the output will not changing, and due to the effect of change in beta also, the output is not changing. It means the Q point is fixed in a particular manner and collector current is independent of temperature variation and change in beta. So it has very good stability. If I talk about fixed bias, it has very poor stability, and if I talk about the emitter bias, it has very good stability compared to the fixed bias circuit. Now, this is too much for today. We will discuss next biasing technique in our next class. Till now, thanks you so much and subscribe.